Hello and welcome back. Settle in, get comfortable, and let your eyes grow heavy whenever they're ready. Tonight we're sitting with a question that sounds simple at first, but opens into something far stranger the longer you hold it. How far could a human being actually travel into space? Not a probe. Not a satellite drifting past some distant moon with no one aboard to see it. A real person, a living crew, pushing outward as far as the laws of physics will ever allow. We won't rush toward the answer. We have 2 hours ahead of us tonight and nowhere else to be, so we'll travel gently, in stages, starting close to home and letting the scale grow slowly from there, until the numbers stop feeling like numbers at all, and start feeling like something closer to wonder. Here's the shape of where we're headed. Human beings have already stepped through one door, leaving this world, standing on another, and returning safely to tell the story. We're standing at the edge of a second door, one we've sent our robotic eyes through, still dreaming of the day astronauts might follow. And far beyond both of those doors sits a final boundary, one that has nothing to do with rockets or fuel, and everything to do with the very structure of the universe itself. By the end of tonight, you'll have a real answer, grounded in actual physics, for how far we could go at every level of technology, and why each new stretch outward costs so much more than the one before it. And underneath the numbers, I hope you're left with something softer too, a quiet sense of scale, and of how fortunate we are to be here at all, wondering about any of this, safe and warm, drifting gently towards sleep. So take a slow breath in and let it go slowly. Let's begin close to home, because even the longest journey starts with a single, modest step. Let's start with the part of this question that already has a real lived answer, because human beings have actually done this part. We've left Earth, travelled through the vacuum of space, and stood on the surface of another world. The moon sits, on average, about 238,000 miles away, or roughly 384,000 kilometers, which is a distance that sounds enormous until you compare it to almost anything else we'll discuss tonight. Light, moving at its famous, unbeatable speed, crosses that gap in about a second and a quarter. If you could drive a car there at highway speed without stopping, it would take you about 6 months. The Apollo astronauts, riding atop the immense controlled violence of a Saturn V rocket, made the trip in roughly 3 days. 3 days! That's worth sitting with for a moment. The only other world that humans have ever physically touched is a 3-day drive away in cosmic terms. It's our porch light. It's the nearby hill we can see from our window. And yet, even at that modest distance, the challenges were extraordinary. A vehicle that had to fight free of Earth's gravity, a fragile capsule for life support, a margin for error so thin that an entire mission, Apollo 13, came within a hair of catastrophe with nothing more than an oxygen tank malfunction. If a journey of 238,000 miles required that much precision, that much expertise, and that much courage, you can begin to feel, intuitively, just how much harder the next steps out would become. Beyond the moon, the next major milestone in human reach is Mars. And here, the distance grows by an order of magnitude that's almost difficult to picture cleanly, because Mars doesn't sit still relative to us. Earth and Mars orbit the Sun at different speeds, on different paths, so the distance between the two planets is constantly changing, breathing in and out like a slow, cosmic tide. At their closest approach, which astronomers sometimes call opposition, Earth and Mars can be as near as about 33 million miles apart, or 54 million kilometers. At their farthest, when the two planets sit on opposite sides of the Sun, that distance balloons to nearly 250 million miles, or about 400 million kilometers. Because spacecraft don't travel in a straight line, but instead follow curving, fuel-efficient paths that loop gently around the Sun, the actual travel time to Mars using current chemical rocket technology tends to fall somewhere between 6 and 9 months, depending on the alignment of the planets and the specific trajectory chosen. 6 to 9 months. Already, that's a different category of challenge than 3 days to the moon. It means the astronauts aboard such a mission would need to bring not just life support, but the means to sustain it, recycle it, and repair it for the better part of a year while floating in a tin can through the vacuum, exposed to far more cosmic radiation than astronauts on the International Space Station currently experience. Because there's no thick magnetic field of Earth wrapped protectively around them anymore. And here, gently, we encounter the first real wall on our journey outward. Not a wall of distance, but a wall of biology. The human body did not evolve for space. It evolved for the very particular conditions of Earth, a steady 1G of gravity pulling blood and bone into familiar shapes. A thick atmosphere filtering out the worst of the Sun's radiation, day-night cycles that set the rhythm of our internal clocks. Take a human being out of that envelope, and the body begins, slowly and quietly, to protest. In microgravity, astronauts lose bone density at a rate that would alarm any doctor on Earth. Something like 1 to 2% per month in certain bones, unless they fight back daily with hours of resistance exercise. Muscles, especially the muscles that fight gravity simply by holding us upright, begin to waste away. Fluids shift upward in the body toward the head, which can cause pressure changes in the eyes and, over long missions, measurable changes in vision. And then there's radiation, outside the protective cocoon of Earth's magnetic field. Astronauts are exposed to a steady rain of high-energy particles from the Sun and from deep space alike, a slow accumulation of risk that grows with every additional month away from home. None of these things make a trip to Mars impossible. Engineers and physicians have spent decades working on countermeasures, exercise regimens, radiation shielding, artificial gravity concepts using rotation, careful mission planning to minimize exposure during periods of heightened solar activity. A Mars mission with enough preparation sits well within what current and near-future technology could plausibly achieve. NASA, along with other space agencies and private companies, has spent years actively designing for exactly this kind of journey, with crewed Mars missions now seriously discussed for some time in the coming decades. But even here, on a journey that's almost within reach, we can already feel the shape of the larger pattern that will define the rest of tonight's exploration. Every additional bit of distance asks for an exponentially larger toll, paid not just in fuel and engineering, but in time, and in the slow wear of the human body against an environment it was never designed to survive in. Before we move past the inner solar system entirely, it's worth a gentle brief detour to the two worlds we haven't yet mentioned. Mercury and Venus, the two planets that orbit closer to the Sun than Earth does, and which present their own particular. Fascinating reasons why human travel there remains far more complicated than the distances alone would suggest. Venus, our nearest planetary neighbour in terms of pure distance, sits at an average of about 25 million miles away, closer to Earth, on average, than even Mars. A spacecraft can reach Venus in a matter of months using current technology, and several robotic missions have done exactly that since the 1960s. But Venus is by a wide margin the most hostile world in our solar system for any visiting human being, despite being similar to Earth in size and structure. Its thick atmosphere, composed mostly of carbon dioxide, traps heat so efficiently that surface temperatures average around 860 degrees Fahrenheit. Hot enough to melt lead, with atmospheric pressure at the surface roughly 90 times that of Earth, equivalent to the crushing pressure found nearly a mile beneath our own oceans. Clouds of sulfuric acid drift through its skies. It is, in almost every sense, a vision of what an uncontrolled greenhouse effect can do to an otherwise Earth-sized world, and it stands as a quiet, sobering reminder of how delicately balanced our own planet's climate truly is. Some researchers have proposed that Venus's upper atmosphere, at an altitude of around 31 miles above the surface, where pressure and temperature happen to closely resemble conditions at Earth's surface, might one day support floating habitats, cities suspended gently within the clouds themselves, rather than any attempt to land on the crushing, scorching surface below. It remains a distant, speculative idea, but a genuinely beautiful one to imagine. Gentle, drifting settlements, suspended in golden Venusian clouds, close enough to see the sun rise and set with unusual brilliance through that thick, swirling atmosphere. Mercury, meanwhile, sits closest to the sun of all, at an average distance of about 36 million miles from it, and somewhere between 50 million and 138 million miles from Earth, depending on where each planet happens to be in its orbit at the time. It's a small, rocky, airless world, similar in some ways to our own moon, baked by the sun on one side, where daytime temperatures can reach upwards of 800 degrees Fahrenheit, while the night side, with no atmosphere to retain any warmth, plunges to nearly 300 degrees below zero. Its extremely slow rotation means a single day on Mercury, from sunrise to sunrise, lasts about 176 Earth days. An almost dizzying thought. A single day longer than half an Earth year. Despite these harsh conditions, Mercury holds a particular, quiet interest for scientists because of the deep, permanently shadowed craters near its poles, regions where sunlight never reaches, and where temperatures remain cold enough, even this close to the sun, that significant deposits of water ice have been detected. A genuinely remarkable discovery on the solar system's hottest world. It's a small, lovely irony, the kind the universe seems to enjoy scattering throughout its design, ice patiently persisting in shadow on the very doorstep of our star. Neither Venus nor Mercury currently feature prominently in serious human exploration plans, not because the distances are prohibitive, they're actually shorter, in many cases, than the distance to Mars, but because the environmental conditions on both worlds are simply far more punishing than anything astronauts would face on the Red Planet. It's a useful reminder, tucked gently here at the edge of the inner solar system, that distance alone never tells the whole story. Sometimes the nearest destination is, in practice, far harder to visit than one considerably farther away, simply because of what waits at the other end of the journey. With that small detour complete, let's continue gently outward, past the asteroid belt, toward the realm of the gas giants, where the character of our solar system and the nature of the challenge ahead of us begins to shift in earnest. Beyond Mars lies the asteroid belt, a wide scattered ring of rocky debris orbiting the Sun roughly between Mars and Jupiter, the leftover rubble from the solar system's early chaotic formation. It's tempting to imagine it the way old films sometimes show it, a dense, dangerous field of tumbling boulders that a ship would have to dodge and weave between. The reality is far gentler, and in its own way a little bit lonelier. The asteroid belt is mostly empty space, with its countless rocky bodies spread so thinly that a spacecraft could often pass through without ever coming close to one. Still, the asteroid belt marks a meaningful psychological threshold. It's the rough boundary between what we sometimes think of as the inner, rocky solar system, home to Mercury, Venus, Earth, and Mars, and the outer solar system, an entirely different kind of neighborhood, dominated by gas giants, icy moons, and distances so vast they begin to make even the gap to Mars look almost cozy by comparison. So let's pause for a moment in this quiet space between the rocky worlds and the giants beyond. We've covered, so far, 2 genuine human achievements and 1 largely autonomous near future with real named missions either already complete or seriously underway. The moon, 3 days away, already visited, already walked upon by 12 human beings between 1969 and 1972. Mars, 6 to 9 months away, technologically within reach, biologically demanding, but not impossible. A goal actively being pursued today. From here, the character of the journey changes. We're about to leave the part of the solar system where current chemical rockets make reasonable sense and step into a realm where the distances grow so large that entirely different propulsion philosophies become necessary, where mission durations stretch from months into years, and then from years into decades, and where the question stops being simply can we build a vehicle that survives the trip and starts becoming can we build a civilization patient enough and clever enough to sustain a crew across timescales that outlast careers and sometimes outlast generations. It's a good moment to notice your own breathing. In, slowly out. Slowly, we're about to leave the warm, familiar glow of the inner solar system behind and head outward into the cold. Past the asteroid belt, the first giant we meet is Jupiter, and here the scale of our journey takes its first truly dramatic leap. Jupiter orbits, on average, about 484 million miles from the Sun, which puts it, depending on planetary alignment, somewhere between 365 million and 600 million miles from Earth at any given time. Light takes around 43 minutes to make that one-way crossing. Using current propulsion technology, robotic probes have made the journey in anywhere from about 6 months. In the case of the New Horizons spacecraft, which used Jupiter for a gravity assist on its way further out, to around 6 years for missions designed to actually slow down and enter orbit, like the Galileo and Juno spacecraft. No human being has ever travelled anywhere near this far. And once you start to imagine what such a journey would require, you understand why. A crewed mission to Jupiter, even using a relatively direct trajectory, would likely take somewhere in the range of 2 to 6 years, depending on the specific path and propulsion method, with current or near-future chemical and ion propulsion. That's not a problem you solve with extra food and water. That's a problem that touches every single aspect of mission design. The psychological toll of years spent in a small enclosed space with the same handful of people. The radiation exposure, which compounds with every additional month outside Earth's protective magnetic field. The sheer mass of supplies, fuel, and redundant systems that must be carried along, since there's no possibility of a quick resupply mission from home. And Jupiter itself isn't particularly welcoming once you arrive. Its intense radiation belts, generated by its powerful magnetic field, are so fierce that even robotic spacecraft have to be carefully shielded and often limit their time in the most dangerous zones. A human crew couldn't simply orbit Jupiter the way astronauts orbit Earth. They'd need to keep a respectful, calculated distance, observing from afar, the radiation simply too intense for anything biological to survive nearby for long. Beyond Jupiter lies Saturn, drifting through space at roughly double Jupiter's distance from the Sun, around 886 million miles out on average. Light takes about 80 minutes to reach Saturn from the Sun. The Cassini spacecraft, one of the most celebrated robotic missions in the history of space exploration, took about 7 years to reach Saturn using a careful series of gravity assists from Venus, Earth, and Jupiter to build up speed along the way. 7 years for a robot with no need to eat, sleep, exercise, or maintain its sanity in isolation. For a human crew, a direct mission to Saturn, even with optimistic propulsion assumptions, would likely require somewhere in the realm of 7 to 10 years round trip, an undertaking that starts to brush up against the length of an entire professional career. And here, a second wall on our journey reveals itself. Not biology this time, exactly, but something closer to it. Call it the wall of time itself, or perhaps the wall of human patience and human lifespan. Think about what it would mean to commit 10 years of your life, the very best, most physically capable years most people have, to a single journey with no certainty of how you'd feel, physically or emotionally, by the end of it. Think about what it would mean to leave behind everyone you love, knowing that letters and messages would take well over an hour to arrive in either direction by the time you reached Saturn, turning every conversation into something closer to an exchange of old letters than a real-time chat. Think about raising children, if you chose to, inside a metal hull, with Earth nothing more than a pale, fading dot in the rearview mirror. These aren't merely engineering problems, they're deeply human problems, the kind that remind us that the greatest obstacle to travelling further into space might not be rockets at all, but rather our own nature as creatures built for one planet, one gravity, one relatively short lifespan, and a deep, evolved need for connection with others nearby. Still, we continue outward, because the question tonight isn't only what's comfortable, but what's possible. So let's keep moving, gently, toward Uranus and Neptune. Uranus orbits at an average distance of about 1,784,000,000 miles from the Sun. Light takes roughly 2 hours and 40 minutes to cross that gap, The Voyager 2 spacecraft, the only mission ever to visit Uranus up close, took about 8.5 years to get there, using a series of gravitational slingshots past the inner giant planets to build up enough speed. Neptune, the outermost of the traditionally recognized planets, sits at an average distance of about 2,793,000,000 miles from the Sun. Light takes about 4 hours and 10 minutes to make that journey. Voyager 2 took roughly 12 years to reach Neptune after its long, looping path through the outer solar system. 12 years for an unmanned probe. If we tried to imagine a crewed mission to Neptune using anything resembling current chemical propulsion, we'd likely be looking at a round trip stretching well beyond 2 decades, even with the most optimistic assumptions about trajectory and technology. 20 years is longer than many careers. It's longer than most marriages last, statistically speaking. It's an entire chapter of a human life spent almost entirely inside a sealed metal vessel, drifting through darkness with sunlight so faint by the time it reaches Neptune that, if you stood on one of its moons and looked up, the sun would appear as little more than an unusually bright star, no longer the warm golden disk we know from Earth, but a cold, distant point of light among countless others. And this is where, very gently, the emotional weight of the journey starts to shift. Because somewhere out past Neptune, the very idea of the solar system as we usually picture it, a tidy diagram of 8 planets circling a star, starts to dissolve into something far stranger and far larger. Beyond Neptune lies the Kuiper Belt, a vast disc-shaped region filled with icy bodies, dwarf planets, and frozen debris left over from the solar system's formation. Pluto resides here, along with countless other small worlds, some named, many still unknown, drifting in the deep cold roughly 3 billion to 4.5 billion miles from the Sun. The New Horizons spacecraft, launched in 2006, took about 9.5 years just to reach Pluto, even travelling faster than any spacecraft launched before it, at speeds exceeding 30,000 miles per hour. Imagine that speed for a moment, 30,000 miles per hour. Fast enough to cross the entire continental United States in about 5 minutes. And even at that extraordinary velocity, it still took nearly a decade just to reach Pluto, and Pluto isn't even the edge of our solar system. Not by a long stretch. Beyond the Kuiper Belt lies an even more distant, more mysterious region, the Oort Cloud. A vast, roughly spherical shell of icy material thought to surround the entire solar system, extending outward possibly as far as 1 to 2 light-years from the Sun. We've never directly observed an object within the Oort Cloud. Its existence is inferred, beautifully and carefully, from the behavior of long-period comets, which seem to originate from precisely this kind of distant surrounding shell. If the Oort Cloud truly extends a full light-year or more from the Sun, then it represents something profound. The outer edge of our solar system reaches nearly a quarter of the way to our very nearest stellar neighbour. The Sun's gravitational influence, weak as it becomes at such distances, still gently shapes the orbits of icy bodies drifting in that far, cold dark, long before you'd reach the gravitational neighbourhood of any other star. Voyager 1, humanity's most distant spacecraft, launched in 1977 and still, remarkably, sending back data today, has been travelling outward for decades and has only just crossed into interstellar space, the region beyond the direct influence of the solar wind. And yet, even after all these decades of travel, Voyager 1 is nowhere close to reaching the inner edge of the Oort Cloud. At its current speed, it would take roughly 300 years just to reach the Oort Cloud's inner boundary, and around 30,000 years to pass entirely through it and out the other side. 30,000 years. Let that number settle for a moment, the way a stone settles slowly to the bottom of a still pond. 30,000 years ago, human beings were only just beginning to paint on the walls of caves in what's now France and Spain. The entirety of recorded human history, every kingdom, every war, every book ever written, every person who has ever lived, fits comfortably within a tenth of that span. And that's merely how long it would take our fastest current spacecraft to cross the outer shell of our own solar system, the very edge of the sun's gravitational reach, not even the beginning of a journey to another star. This is the moment in our exploration where the numbers stop behaving like ordinary numbers and start behaving like something closer to poetry, or perhaps closer to prayer. We're no longer just measuring distance. We're measuring the gap between a single human lifetime and the patient, indifferent scale of the universe itself. And we haven't even left home yet. Not really. Everything we've discussed so far, the Moon, Mars, Jupiter, Saturn, Uranus, Neptune, the Kuiper Belt, even the distant Oort Cloud, all of it still lies within the gravitational embrace of our own sun. We've been touring our own house, room by room, and only now, slowly, are we approaching the front door. Beyond that door lies interstellar space. And beyond interstellar space lie the stars themselves. Let's rest here for just a moment before we step through. Take a breath. Notice the weight of your body, settled comfortably wherever you're resting tonight. There's no rush. The stars have been waiting billions of years already. They can wait a little longer while you get comfortable. So here we are, standing in our imagination at the very threshold of interstellar space. Behind us, the sun has shrunk to little more than a bright star among many. Ahead of us lies an ocean of dark, nearly empty space, stretching out toward our nearest stellar neighbours. The nearest star system to our own is Alpha Centauri, a triple star system containing two sun-like stars orbiting closely together, Alpha Centauri A and B, along with a smaller, dimmer red dwarf called Proxima Centauri, which happens to be, ever so slightly, the closest of the three to us. Proxima Centauri sits about 4.24 light-years away. Now, a light-year is simply the distance light travels in 1 year, moving at its constant, unbeatable speed of about 186,000 miles per second, or roughly 670 million miles per hour. In a single year, light covers about 5.8 trillion miles. So when we say Proxima Centauri is 4.24 light-years away, we mean it's light. The light you'd see if you looked at it through a telescope tonight left that star over 4 years ago. We mean the actual physical distance between us and that star is somewhere around 25 trillion miles. 25 trillion miles. It's worth trying, gently, to feel the size of that number, even though our minds aren't really built for it. If you could drive there in a car at highway speed without ever stopping for gas, sleep or rest, the journey would take about 40 5 million years. If you boarded the fastest crewed spacecraft humanity has ever built, the Apollo command modules that carried astronauts to the moon, which reached speeds of about 25,000 miles per hour on their return to Earth, the trip to Proxima Centauri would still take over 100,000 years. This is the moment where our journey tonight shifts from engineering challenge to something closer to fundamental limit of what current human technology can achieve. We are no longer simply asking for more fuel, more time, more patience. We're asking for an entirely different category of propulsion, a different relationship between energy and speed than anything humanity has yet built. So let's talk slowly and gently about the different tiers of propulsion technology that scientists and engineers have proposed for interstellar travel. Because each tier unlocks a dramatically different version of how far could humans go, and each tier comes with its own profound challenges. The first tier is what we might call chemical propulsion. The same basic technology that carried astronauts to the moon and rovers to Mars. Chemical rockets work by burning fuel and expelling the resulting gas at high speed out the back of the engine, pushing the spacecraft forward in the opposite direction, the same basic principle as a balloon zipping across a room when you let go of it unsealed. Chemical propulsion is reliable, well understood, and has carried every human being who has ever left Earth. But it's also, fundamentally, quite weak. In cosmic terms, even our most powerful chemical rockets top out at speeds far too slow to make interstellar travel practical within a human lifetime. Which is exactly why the Proxima Centauri journey, using this kind of propulsion, stretches into the 100,000-year range. The second tier involves nuclear propulsion, a category that includes several different proposed approaches. Nuclear thermal propulsion uses a nuclear reactor to superheat a propellant, like hydrogen, expelling it at much higher speeds than chemical combustion can achieve, potentially doubling or tripling the efficiency of conventional rockets. A more exotic variant, sometimes called nuclear pulse propulsion, and explored seriously in the mid-20th century under a project named Orion, proposed detonating a series of small nuclear explosions behind a heavily shielded spacecraft, using each blast to push the craft forward in controlled rhythmic pulses. It sounds almost like science fiction, and in many ways the political and safety concerns alone have kept it firmly theoretical. But the physics behind it is sound, and calculations suggest such a vehicle could theoretically reach speeds up to about 10% of the speed of light. 10% of light speed. At that velocity, the journey to Proxima Centauri would take somewhere around 42 years. Still longer than most careers, but suddenly, for the first time in our exploration tonight, within the realm of a single human lifetime. A crew that departed in their 20s or 30s could plausibly arrive while still alive, though considerably older, having spent the majority of their adult years in transit. The third tier moves into something even more theoretical, but still grounded in real physics: nuclear fusion propulsion. Unlike the nuclear fission used in current reactors and weapons, fusion involves combining light atomic nuclei like hydrogen into heavier ones, releasing tremendous amounts of energy in the process, the same basic reaction that powers the sun itself. We don't yet have working fusion reactors that produce more energy than they consume here on Earth, though research continues steadily, with promising progress over the past several years. But if fusion propulsion were achieved, calculations from projects like the British Interplanetary Society's Project Daedalus, a detailed theoretical study from the 1970s, suggest speeds of up to 12% of light speed might be achievable, using massive, unmanned probes designed to study nearby star systems. At 12% of light speed, the trip to Proxima Centauri would take around 35 years. Closer still to a manageable span of human life, though still representing the bulk of an adult's working years, spent entirely in transit, sealed inside a vessel, with no possibility of resupply, repair from outside help, or rescue if something goes wrong. The fourth tier, and here we begin drifting properly into the territory of theoretical physics rather than near-future engineering, involves concepts like antimatter propulsion. When matter and antimatter meet, they annihilate each other completely, converting their entire mass directly into energy, following Einstein's famous equation relating mass and energy. It's the most efficient form of propulsion theoretically possible using conventional physics, far more efficient than fusion or fission. The challenge, and it's an enormous one, is that we currently know how to produce only the tiniest, most minuscule quantities of antimatter at staggering cost and energy expenditure using particle accelerators. Producing enough antimatter to fuel an interstellar journey would require, by some estimates, centuries of dedicated global production at our current technological capability. And finding a way to store and contain that antimatter safely without it touching any normal matter and triggering catastrophic energy release remains an unsolved engineering puzzle. Still, in theory, antimatter propulsion could potentially push spacecraft to a meaningful fraction of light speed, perhaps as high as 50% or more, depending on the specific design and how much of the ship's mass could be devoted to propellant versus payload. At 50% of light speed, the journey to Proxima Centauri would take roughly 8.5 years. From the perspective of someone watching from Earth. And here, gently, we arrive at one of the strangest and most genuinely wondrous parts of tonight's exploration. The idea that, at speeds approaching a meaningful fraction of light, time itself begins to behave differently for the people making the journey than it does for those left behind. This isn't speculation or a clever turn of phrase. It's one of the most rigorously tested predictions in all of physics, a direct consequence of Einstein's theory of special relativity, confirmed again and again through nearly a century of experiments, from atomic clocks flown on airplanes to the satellites that make your phone's GPS function correctly every single day. The faster an object moves relative to an observer, the slower time passes for that object from the observer's point of view. And the effect isn't gentle and gradual. It's negligible at the speeds we're used to, the speed of a car, a plane, even Voyager 1. But it grows dramatically, almost explosively, as you approach the speed of light. At 50% of light speed, the effect is real but moderate. Time for the crew would run only slightly slower than time back on Earth, perhaps experiencing the 8.5-year journey as something closer to 7.5 years aboard ship. But push the speed higher, into the 90% range, and the effect becomes extraordinary. At 90% of light speed, time aboard a spacecraft would pass at less than half the rate it passes on Earth. At 99% of light speed, that ratio stretches even further, time aboard ship moving at roughly 1/7 the rate experienced back home. Push to 99.9% and the ratio becomes more than 1 to 20. What this means, practically and almost magically, is that a sufficiently advanced spacecraft capable of sustaining acceleration close to the speed of light for extended periods could carry a human crew not just to Proxima Centauri, but potentially much, much farther. Within the span of a single human lifetime, as experienced by the travelers themselves, even though, from the perspective of the people they left behind on Earth, the journey would still take a far longer span of years, decades, centuries, or more. This is the principle behind a concept sometimes called a relativistic rocket, a theoretical vehicle capable of sustaining a constant, gentle acceleration roughly equivalent to Earth's own gravity for the entire duration of a journey, first accelerating for the first half of the trip, then flipping around and decelerating for the second half, arriving gently at the destination rather than blazing past it. Using this kind of constant acceleration, calculations suggest that a crew could reach Proxima Centauri, experiencing roughly 3.5 years of subjective time aboard ship, even though more than 4 years would pass back on Earth. Push further, and the possibilities become almost dizzying. The same constant acceleration approach could theoretically carry a crew to the center of our own galaxy, a journey of about 26,000 light-years as measured from Earth, in roughly 20 years of subjective time experienced by the travelers, even though, from Earth's perspective, 26,000 years would pass during the journey, and humanity itself might look entirely different, if it still existed at all, by the time anyone back home could even confirm the ship had safely arrived. We'll come back to this remarkable, almost dreamlike property of the universe a little later tonight, because it deserves more careful unpacking. But for now, let it simply settle into your mind like a stone sinking gently through still water. Distance and time are not as separate or as fixed as they feel in ordinary daily life. They bend, together, in the presence of sufficient speed. And that bending is not a flaw in the universe, or a strange coincidence. It's one of its deepest and most elegant features. For now, let's return to something a little more grounded, a little more practical. Because even setting aside the wonders of relativity, there remain very real, very physical barriers standing between human beings and any meaningful journey to another star. Before we move further outward, it's worth lingering a little longer on something we touched on briefly. What daily life would actually feel like for a crew making any of these long journeys, whether to Saturn, to Proxima Centauri, or beyond? It's easy, when discussing distances and propulsion systems, to focus entirely on the numbers, and forget that every single one of those numbers represents real people, living real days one after another inside a sealed metal vessel. Imagine waking up on what your ship's calendar calls morning, though there's no sunrise to greet you, only the same soft, even artificial light that's greeted you every day for months, or years. You'd likely begin with exercise, a long, almost sacred ritual aboard any extended space mission. because without it, your bones and muscles would slowly, quietly waste away in the gentle absence of gravity. Astronauts aboard the International Space Station today spend roughly 2 hours daily on specialized equipment, treadmills with harnesses to hold them down, resistance machines that use vacuum cylinders instead of weights, all in the patient, ongoing effort to convince a body evolved for Earth's gravity that it still needs to maintain its strength. After exercise, perhaps a meal, likely some combination of rehydrated, shelf-stable food and whatever could be grown aboard ship. Since carrying enough food for a multi-year journey would be impossibly heavy, meaning any truly long mission would need to incorporate some form of onboard agriculture, small gardens of leafy greens perhaps, grown under careful artificial light, both for nutrition and for the simple, quiet psychological comfort of green, living things in an otherwise metal and plastic environment. Then, work, maintenance, mostly, on a vessel where every single system, air recycling, water purification, temperature regulation, radiation shielding, represents a potential point of failure. Hundreds of millions of miles from the nearest hardware store or repair technician. Research, perhaps, depending on the mission's scientific goals. And then, in whatever time remained, the simple, profoundly important work of staying sane, conversation, reading, music, perhaps games. Anything that allows the mind some relief from the unchanging sameness of the view outside every window, which, on the longest journeys, would eventually show nothing at all except an unchanging field of distant, unmoving stars. Psychologists who study isolation, drawing on research from Antarctic research stations, submarine crews, and the International Space Station, have identified a recurring pattern in long-duration missions, sometimes called the third-quarter phenomenon, where morale tends to dip hardest not at the beginning of a difficult mission, where novelty and purpose still feel fresh, and not at the very end, when the finish line becomes visible, but somewhere in the long, featureless middle, when the destination still feels impossibly far away and the routine has fully calcified into monotony. For a 6-month mission to Mars, that difficult middle stretch might last a matter of weeks. For a multi-year journey to Saturn, or a multi-decade journey to a nearby star, that same psychological dip could stretch on for a very long time indeed, which is part of why mission planners take crew psychology every bit as seriously as fuel calculations and radiation shielding. There's also the quieter, more existential weight of distance itself. Something astronauts who've travelled even as far as the moon have described in surprisingly similar terms. The Apollo astronauts spoke again and again of a particular, almost overwhelming feeling that came from looking back and seeing Earth, their entire home, their entire species, every person they'd ever loved, shrink down to a small, fragile blue marble suspended in an ocean of black. Some described it as a profound, almost spiritual experience. A sudden, visceral understanding of how small and precious our planet truly is. It's been given a name since, the overview effect, a shift in perspective that seems to occur reliably in astronauts who've had the chance to see Earth from a genuine distance. Now imagine that same feeling, but stretched across a journey where Earth doesn't just shrink to the size of a marble, but eventually shrinks to nothing more than an indistinguishable point of light, lost among countless other points of light, no longer visibly different from any other star in the sky. For a crew travelling toward Proxima Centauri, there would likely come a day, somewhere in the middle of the journey, when Earth, the Sun, and the entire solar system simply became too distant and too dim to pick out at all, even with the ship's best instruments. A profound, quiet, almost unbearably moving moment. If you let yourself sit with it, the day home stopped being a place you could point to, and became instead simply a memory, a story, a feeling, carried forward in the absence of any visible reminder. It's worth saying gently that none of this is meant to frighten you, here in the safety and warmth of wherever you're resting tonight. It's meant instead to add a little more texture, a little more humanity to the numbers we've been discussing. Behind every figure, every light year, every calculated year of travel time, there would be real people, brushing their teeth in zero gravity, missing the smell of rain, laughing quietly at old jokes, slowly building an entirely new kind of life inside the strange, narrow confines of a vessel built to carry them farther than any human being has ever gone. Now let's widen our view again, gently, and consider where exactly such a crew might be headed, because Proxima Centauri, while our nearest stellar neighbour, is very far from being the only star worth considering. Alpha Centauri A and B, the two larger, Sun-like companions to small, dim Proxima Centauri, sit at almost exactly the same distance, about 4.3 to 4.4 light-years away, close enough that any mission capable of reaching Proxima Centauri could, with only slight adjustments, reach either of these two stars instead. Alpha Centauri A in particular is strikingly similar to our own Sun, similar in size, similar in temperature, similar in the soft yellow-white colour of its light, which has made it a particularly popular subject of speculation among scientists and writers alike, wondering what kind of planets, if any, might orbit a star so familiar in character, so unfamiliar in location. A little farther out, at about 6 light-years, lies Barnard's star, a small, dim red dwarf notable mostly for moving unusually quickly across our sky relative to other stars, a result of its relatively close proximity combined with its particular trajectory through the galaxy. At roughly 8.6 light-years, we find Sirius, the brightest star visible in Earth's night sky. A brilliant blue-white star considerably larger and hotter than our Sun, accompanied by a small, incredibly dense white dwarf companion, the collapsed remnant of a star that burned through its fuel long ago. Further out still, at around 10.5 light-years, sits Epsilon Eridani, a young sun-like star that's drawn particular interest from astronomers because it's known to host at least one confirmed planet, along with what appear to be 2 asteroid belts and an outer disk of icy debris, not unlike a miniature, slightly younger version of our own solar system. And at about 11.9 light-years, we reach Tau Ceti, another sun-like star, one of the closest single stars similar in type to our own, long a subject of fascination in both serious scientific study and popular science fiction, partly because of its relative similarity to the Sun, and partly because of tentative evidence suggesting it may host several planets, some falling within what astronomers call the habitable zone, the comfortable range of distance from a star where conditions might allow liquid water to exist. Each of these stars represents a slightly different version of the same underlying journey we've been discussing all night, a few more light years here. A star slightly more or less similar to our own there, but fundamentally governed by the very same physics, the very same propulsion challenges, the very same profound questions about biology, patience, and time. Whether a future human crew set their sights on Proxima Centauri, Alpha Centauri A, Sirius, or Tau Ceti, the character of the journey would remain remarkably similar. Years or decades of travel, profound psychological and biological challenges, and, if sufficiently advanced relativistic propulsion were ever achieved, that same strange, generous gift of time dilation, softening the subjective burden of the years required. It's a gentle reminder that our nearest stellar neighbours, while individually distinct, with their own colours, their own sizes, their own particular stories, are, in the context of the entire galaxy, huddled together in a tiny, almost cosy little cluster, all within roughly a dozen light years of our Sun. A neighbourhood so small, on a galactic scale, that it would barely register as a single point if you zoomed out far enough to see the Milky Way's true size, a disk of stars stretching some 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars in total, of which the handful we just mentioned represent only the very closest, faintest whisper of a much, much larger chorus. Let's talk gently about energy, because energy is, in many ways, the true currency of space travel. Every single mile a spacecraft covers has to be paid for, not in money, but in fuel. And the faster you want to go, the more disproportionately expensive that fuel becomes. There's a famous piece of mathematics in rocketry called the rocket equation, first worked out in a clean, elegant form by the Russian scientist Konstantin Tsiolkovsky back in 1903, decades before anyone had actually launched anything into space. The rocket equation describes a frustrating, almost cruel relationship between a spacecraft's final speed and the amount of fuel it needs to carry. In simple terms, because a rocket has to carry all of its own fuel with it, and because that fuel itself has mass, and because accelerating that mass requires yet more fuel, the relationship between speed and required fuel isn't a straight line. It's closer to a curve that bends sharply upward so that each additional bit of speed costs exponentially more fuel than the speed before it. This is part of why, even with extremely advanced propulsion concepts, reaching a high fraction of light speed becomes so punishingly difficult. If you wanted to accelerate a spacecraft and everything aboard it, including the crew, their supplies, their living quarters, and their water and air recycling systems, to even 10% of light speed, using current chemical or even advanced nuclear propulsion, the amount of fuel required would dwarf the mass of the spacecraft itself many times over, to the point of becoming wildly impractical. This is why concepts like antimatter propulsion, or theoretical ideas like the Bussard ramjet, which imagines a spacecraft scooping up hydrogen atoms, drifting through interstellar space and fusing them for fuel as it travels, so it doesn't have to carry all its fuel from the start, generate so much excitement among physicists and engineers. They represent ways of trying to sidestep the worst implications of the rocket equation. But each comes with its own profound, currently unsolved challenges. Antimatter remains essentially impossible to produce or store in meaningful quantities. The Bassard ramjet concept, while elegant on paper, runs into serious problems when you calculate the actual density of hydrogen atoms in interstellar space, which turns out to be so sparse that the drag created by collecting it might cancel out much of the benefit. A problem that's kept the concept firmly in the realm of theory since it was first proposed in 1960. There's also a concept that doesn't rely on carrying fuel at all, at least not in the traditional sense. The idea of a light sail, sometimes called a solar sail, or in more advanced interstellar proposals, a laser sail. The basic principle is wonderfully simple and almost poetic. Light itself carries a tiny amount of momentum, and when light reflects off a surface, it imparts a small push. A sufficiently large, sufficiently thin, and sufficiently reflective sail, pushed by an enormously powerful laser array based either on Earth or in space, could theoretically be accelerated to a significant fraction of light speed without needing to carry any fuel at all, since the energy source stays behind, beaming light outward toward the departing craft. This is the basic concept behind Breakthrough Starshot, a real research initiative announced in 2016, which proposes sending a fleet of tiny postage stamp-sized probes, each attached to a lightweight sail just a few meters across, toward Alpha Centauri using a massive ground-based laser array. The theoretical goal is to accelerate these tiny probes to around 20% of light speed, which would allow them to reach the Alpha Centauri system in just over 20 years. It's an audacious, beautiful idea, and entirely plausible in principle, though enormous engineering challenges remain unsolved, including how to build a laser array powerful enough, how to keep the beam precisely focused across millions of miles, and how to ensure the tiny probes survive collisions with interstellar dust at such extraordinary speeds. Notice, though, that even this approach, one of the more promising and actively researched interstellar concepts, is designed for tiny, unmanned probes, not human crews. Scaling the same approach up to carry a living crew, along with everything they'd need to survive, introduces mass requirements so much larger that the same laser sail approach becomes vastly less practical, at least with technology we can currently imagine building. Which brings us to a different, older idea entirely, one that sidesteps the speed problem by embracing the slowness instead: the generation ship. The concept is exactly what it sounds like. Instead of trying to build a vessel fast enough to reach another star within a single human lifetime, you build a vessel large enough and self-sustaining enough to support an entire community indefinitely across multiple generations, with the original crew's grandchildren or great-grandchildren eventually arriving at the destination, having been born, raised, and grown old entirely aboard ship, having never set foot on a planet at all. It's a beautiful idea in some ways and a deeply unsettling one in others, and it's worth sitting with both feelings honestly tonight rather than rushing past either. The beauty lies in the audacity of it. An entire self-contained civilization drifting silently through the dark for centuries, carrying not just supplies and equipment, but culture, language, music, memory, and hope across a gulf of space and time that no single human being could ever cross alone. Some proposals imagine vast, rotating, cylindrical habitats, generating artificial gravity through their spin, with farmland, forests, and small towns built along their curved inner surfaces, a self-contained miniature Earth, sealed inside a metal shell, drifting toward a star that the original builders would never live to see. The unsettling part lies in the sheer scale of what such a project would demand. A truly self-sustaining generation ship would need to solve problems that, frankly, we haven't fully solved even here on Earth. With an entire planet's worth of resources at our disposal, closed-loop ecosystems that can recycle air, water, and nutrients indefinitely, without slow. Accumulating failures, genetic diversity sufficient to avoid the serious health problems that come from a small, isolated population reproducing across many generations, social and political structures stable enough to survive centuries of enclosed life without collapsing into conflict, despair, or simple loss of purpose, and a level of engineering redundancy so thorough that the ship could survive not just the original crew's lifetime, but the lifetimes of their children, grandchildren, and great-grandchildren, any one of whom might, through accident, neglect, or simple entropy, introduce a fatal flaw into a system with no possibility of outside rescue or resupply. There's also a profound psychological question buried inside the generation ship idea, one that researchers in space psychology have written about thoughtfully. What does it mean to be born into a journey you never chose, on a ship you'll never leave, traveling toward a destination you may never see? The original crew, presumably, would volunteer, fully aware of what they were committing to. But their children, and their children's children, would have no such choice. They would simply be born, live, and likely die, aboard a metal vessel drifting through the dark, their entire lives spent in service of a goal chosen by ancestors they may never have known. It's not a reason to dismiss the concept. Human beings have, throughout history, been born into all kinds of circumstances they didn't choose and have found meaning, purpose, and even joy within them. But it's a genuinely profound question, and one worth sitting with quietly, the way we're doing now, rather than glossing over. Some researchers have proposed an alternative that sidesteps at least some of these generational concerns: suspended animation, sometimes called hibernation or torpor, in which crew members would be placed into a deep, slowed metabolism sleep for the bulk of the journey, aging only a fraction as much as the actual elapsed time, and waking only as the ship approaches its destination. It's a concept borrowed, in part, from observations of animals here on Earth that hibernate through winter, slowing their metabolism dramatically to conserve energy and reduce biological wear. NASA and other research groups have studied torpor-inducing techniques for potential use on long Mars missions, using methods like therapeutic hypothermia, already used in some medical contexts, to lower body temperature and metabolic rate. For interstellar journeys, true long-term hibernation across years or decades remains firmly theoretical, not yet demonstrated safely in humans for anything beyond short medical procedures. But if it could be achieved safely, it would solve, or at least soften, many of the generation ship's hardest problems. A smaller crew could make the journey directly, aging only slightly during transit, without the immense complexity of supporting multiple generations, farmland, and a self-contained society for centuries. Whichever approach one imagines, generation ships, suspended hibernation, or theoretical relativistic vessels approaching the speed of light, we keep circling back to the same underlying truth. The distance to even the nearest star is so large that crossing it, with anything resembling current or near-future technology, asks something of us that goes far beyond engineering. It asks for patience measured in decades or centuries. It asks for a willingness to commit entire lives or entire family lines to a single, irreversible journey. It asks us to imagine forms of courage and sacrifice that most of human history simply never required, because no one before us ever had the means or the need to ask these particular questions at all. And remember gently that Proxima Centauri, our very nearest stellar neighbour, is just the first star on a map containing hundreds of billions more scattered across our galaxy alone, with countless other galaxies stretching out beyond that, each one separated from us by gulfs of space so large that even light years start to feel like an inadequate unit of measurement. Let's rest here again for a moment. Breathe in slowly. Let your body settle further into wherever you're resting. We're about to step even further outward, toward the true final boundary that governs everything we've discussed tonight, the speed of light itself, and why, as far as we currently understand the universe, nothing made of matter can ever cross it. So let's talk, slowly and carefully, about the speed of light, because it sits at the very heart of tonight's question, and understanding it properly is one of the most satisfying things physics has to offer. Light travels at exactly 299,790,2458 meters per second, a number so precise that it's no longer measured, but defined, used as the very basis for how we define the meter itself. In more familiar terms, that's about 670 million miles per hour, or roughly 186,000 miles every single second. For most of human history, there was no particular reason to think this number was special, beyond simply being very fast. But in 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that quietly, permanently changed our understanding of space, time, and motion itself. Special relativity, as the theory came to be known, revealed something genuinely strange about the universe. The speed of light isn't just fast. It's a fundamental speed limit woven into the very structure of space and time that nothing with mass can ever reach, let alone exceed. Here's the gentle, intuitive version of why. As an object with mass moves faster and faster, accelerating ever closer to the speed of light, its effective mass, from the perspective of the energy required to accelerate it further, increases, not its physical size, but its inertia, its resistance to acceleration. Push a spacecraft to 90% of light speed, and it takes far more energy to nudge it just a little faster than it took to get it from a standstill to 10% of light speed in the first place. Push it to 99%, and the energy required for each additional fraction of a percent grows even more extreme. As you approach 100% of light speed, the energy required to continue accelerating approaches infinity. Infinite energy. That's not a practical engineering hurdle, the kind that future technology might eventually solve with cleverness and persistence. It's a mathematical wall, baked into the very geometry of space-time, that no amount of future ingenuity can simply engineer around, at least not while obeying the physics we currently understand to be true. Physics that has been tested and confirmed, again and again, with extraordinary precision, for over a century. This is why every propulsion concept we discussed earlier, no matter how advanced, antimatter, fusion, laser sails, relativistic rockets, can only ever approach the speed of light, asymptotically getting closer and closer, like a curve that bends ever nearer to a line it can never quite touch, but never actually reaching it, and certainly never exceeding it. It's worth pausing here to gently dismantle a common piece of confusion, because it's an understandable one. People sometimes ask whether faster-than-light travel might be possible through some loophole, some clever trick that future physicists haven't yet discovered. And the honest answer is, we don't fully know what we don't know, and history has shown that physics sometimes reveals genuine surprises. But within the framework of relativity as it currently stands, tested across more than 100 years of experiments, from particle accelerators to atomic clocks, to the behavior of light itself bending around massive objects exactly as predicted, there is no known mechanism by which an object with mass can be accelerated past the speed of light using conventional propulsion. There are, admittedly, some genuinely fascinating theoretical loopholes that get discussed seriously in physics. One's worth mentioning here, gently, because they capture the imagination so beautifully, even though every single one of them currently exists only on paper, in the form of mathematics, with no known way to actually build the things they describe. The most famous of these is the concept of a wormhole, a theoretical shortcut through space-time itself, connecting two distant points via a kind of tunnel, allowing a traveller to cross enormous distances without ever actually exceeding the speed of light locally. Because the trick isn't travelling faster, but rather shortening the distance that needs to be travelled at all. Wormholes emerge as mathematically valid solutions to Einstein's equations of general relativity, which is genuinely remarkable. But creating or maintaining one, if it's even possible, would likely require exotic forms of matter with negative energy density, something that has never been observed to exist in any meaningful quantity, and may not be physically achievable at all. A related, equally theoretical idea is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, which imagines a spacecraft sitting still locally inside a bubble of normal flat space-time, while the space behind the bubble expands and the space ahead of it contracts, effectively carrying the bubble and everything inside it across vast distances without the ship itself ever locally exceeding the speed of light. It's an elegant idea, and it does emerge as a mathematically valid solution within general relativity, much like the wormhole. But just like the wormhole, it appears to require exotic matter with negative energy density to function, along with energy requirements that in early calculations exceeded the entire mass energy of the observable universe, though later refinements have reduced this requirement substantially, even if it remains, by any practical measure, entirely out of reach. So we hold these ideas the way we might hold a beautiful, distant dream, not dismissively, because genuine, serious physicists continue to study them, and because the history of science is full of ideas that once seemed permanently impossible before they weren't. but also not as a basis for any practical plan. Because as far as we can currently tell, with everything we know and have tested about the universe, the speed of light remains an absolute, unbreakable boundary for anything made of ordinary matter, humans very much included. Given that boundary, let's return to the question of how far a human crew could realistically, plausibly travel using the most optimistic but still physically grounded propulsion concepts we discussed earlier: nuclear pulse propulsion, fusion propulsion, antimatter propulsion, or relativistic rockets capable of sustained, gentle acceleration over very long periods. If we imagine a spacecraft capable of accelerating at a steady 1g, the same acceleration as Earth's gravity, which would also conveniently provide the crew with something resembling normal gravity throughout the journey, for half of the trip, then decelerating at the same rate for the second half, calculations show something genuinely remarkable. Within a single human lifetime, say around 50 years of subjective time experienced by the crew themselves, such a vessel could theoretically travel extraordinarily far. Because as speed increases toward the speed of light, the relativistic time dilation effect we discussed earlier becomes more and more pronounced, allowing the crew to experience far less elapsed time than an observer back on Earth would measure. Under this kind of sustained, constant acceleration, a journey of around 12 years of subjective shipboard time could theoretically carry a crew not just to Proxima Centauri, but considerably beyond it, perhaps reaching stars dozens of light years away as measured from Earth, even though only a dozen years would have passed for the travelers themselves. Extend that subjective journey to around 20 or 30 years, still well within a human lifetime, and calculations suggest a crew could theoretically reach distances measured not in mere light years, but in thousands of light years, potentially crossing a meaningful portion of our entire galaxy, at least in principle. Given a propulsion system capable of sustaining that kind of acceleration for that long, which remains, it must be said clearly and honestly, far beyond anything we currently know how to build. This is the strange, beautiful, almost paradoxical answer at the heart of tonight's question, in terms of subjective, lived human experience. The limit on how far a person could travel isn't really set by distance at all. It's set by how close to the speed of light we can get, and for how long we can sustain that speed. Because time dilation means that from the traveler's own perspective, almost any distance becomes survivable within a human lifetime, given enough velocity. But, and this is the crucial grounding piece that keeps this from becoming simple fantasy, from the perspective of everyone left behind on Earth, the actual elapsed time would still be enormous, often vastly larger than a human lifetime, sometimes larger than the entire span of recorded human history. A crew that travels 26,000 light years to the galactic core, experiencing only 20 years of subjective time themselves, would return, if they returned at all, to an Earth that had aged 52,000 years in their absence. An Earth where every person they once knew, and likely entire civilizations, languages, and cultures, would have lived, died, and been forgotten many times over. This is sometimes called the twin paradox, named for a classic thought experiment in which one twin stays on Earth while the other travels at relativistic speed and returns to find their sibling has aged dramatically more than they have. It's not actually a paradox in the sense of being a contradiction, despite the name. It's a real, measured, repeatedly confirmed consequence of how our universe works, demonstrated in miniature through experiments with atomic clocks flown on fast-moving aircraft, which really do tick, ever so slightly more slowly than identical clocks left on the ground. So when we ask how far could humans ever travel in space, the honest, complete answer turns out to have two true faces, both equally real, both grounded in the same physics. From the perspective of the traveler, given sufficiently advanced propulsion capable of sustaining near-light speed for years or decades, the theoretical reachable distance is almost unimaginably large, potentially spanning much of our galaxy within a single lifetime. From the perspective of everyone and everything left behind, including the Earth, the Sun, and the entire familiar world the travellers once called home, that same journey would consume spans of time so enormous that the very meaning of returning becomes uncertain, since there might be nothing recognizable left to return to. This is the climax of tonight's exploration. The place where all the smaller, more practical questions we've been gently working through, fuel, biology, generation ships, propulsion technology, finally converge into a single profound realization. The limit on human travel through space isn't really one limit at all. It's two limits, layered on top of each other, working together. There's the limit of what propulsion technology and physics will allow, a limit that grows more generous, strangely, the closer you push toward the speed of light, because of how time dilation bends the traveler's own experience of the journey. And there's the limit of what it means to remain connected to home, to history, to the rest of humanity, a limit that grows more severe the closer you push toward that very same speed, because the gulf between the traveller's experience and everyone else's stretches wider and wider, until, at extreme enough speeds, a returning traveller would essentially be stepping not into their own future, but into someone else's entirely different, unrecognizable era. There's one more layer to this question, gentler now, slower, but important, because it reveals the true final boundary on how far anything, human or otherwise, could ever travel, no matter how advanced the technology, no matter how close to the speed of light we manage to push, no matter how much subjective time dilation worked in our favor. That boundary isn't propulsion. It isn't biology. It isn't even the speed of light itself exactly. It's the expansion of the universe. Here's the gentle version of a genuinely strange cosmic fact. Space itself is expanding. Not objects moving through a fixed static space, the way a car moves across a parking lot, but the very fabric of space. The distance between things growing larger over time, everywhere, all at once. Like the surface of a balloon slowly inflating, with every point on its surface gradually moving away from every other point. Not because anything is moving across the balloon's surface, but because the surface itself is stretching. This expansion was first discovered observationally in the late 1920s, when astronomer Edwin Hubble noticed that distant galaxies appeared to be moving away from us, and that the farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, has been confirmed and refined countless times since, and it leads to a conclusion that sounds almost like a riddle. The more distant a galaxy is, the faster the space between us, and it is stretching. And here's where things become genuinely strange, in the best, most wonder-filled sense of that word. Because space itself is expanding, there exists a distance out there in the universe, beyond which galaxies are receding from us faster than the speed of light. Now, take a breath, because this isn't a violation of Einstein's speed limit, even though it sounds like one at first. The speed limit imposed by relativity applies to objects moving through space. It says nothing about space itself stretching. A galaxy sitting at extreme cosmic distance isn't moving through space at faster than light speed. Rather, the space between us and that galaxy is growing so quickly that the distance increases faster than light could cross it, even though the galaxy itself, locally, within its own little patch of space, isn't moving especially fast at all. This leads us to one of the most genuinely humbling concepts in all of cosmology: the cosmic event horizon. It marks the boundary beyond which, no matter how fast we travelled, no matter how close to the speed of light we managed to push a spacecraft, we could never, ever reach. Because the space between us and anything beyond that horizon is expanding faster than we could ever cross it, even at the absolute maximum speed the universe allows. Current estimates place this cosmic event horizon at around 16 billion light-years away, though the precise figure depends on the details of cosmological models and continues to be refined as our measurements improve. Beyond that boundary lies a portion of the universe that is, and will forever remain, permanently, physically unreachable to us. Not because we lack the technology, not because we lack the patience or the courage, but because the universe itself has placed those regions forever beyond our grasp, receding faster than light could ever close the gap. This is worth sitting with for a long, quiet moment, because it reframes the entire question we've been exploring tonight. Earlier, when we discussed the difficulty of reaching even the nearest star, it felt like a problem of insufficient technology, something that future engineering, given enough centuries, might eventually solve. But the cosmic event horizon is different. It's not a technological limit. It's a structural feature of the universe itself, as fundamental and unchangeable as the speed of light. No future civilization, no matter how advanced, no matter how many millennia they have to work with, could ever cross it. Because the very destination they're trying to reach is receding faster than any ship could approach it. And there's a further, even gentler layer to this same idea, one that adds a quiet kind of poignancy to everything we've discussed tonight. As the universe continues to expand, and as that expansion appears, based on current observations, to be accelerating, more and more galaxies will cross beyond our cosmic event horizon as time goes on. Distant galaxies that are visible to us today, faint smudges of light captured by our most powerful telescopes, will, over the unimaginably long timescales of cosmic time, eventually recede beyond the point where their light can ever reach us again. Billions of years from now, an observer looking out from our region of the universe would see far fewer galaxies than we see today. Not because those galaxies have disappeared, but because they will have drifted beyond the reach of light itself, swallowed not by darkness, but by the relentless, gentle stretching of space. So when we ask, tonight, what is the absolute furthest a human being could ever travel in space, the complete layered answer looks something like this. With current technology, the realistic limit sits somewhere around Mars, perhaps the outer planets with significant investment in life support and propulsion improvements, journeys of months to a few years. With near-future technology, nuclear propulsion, perhaps early fusion concepts, the realistic limit might extend to the outer solar system, journeys of years to a couple of decades, demanding extraordinary commitment but remaining within a human career, if not entirely comfortable. With highly advanced, currently theoretical technology, fusion or antimatter propulsion capable of reaching a meaningful fraction of light speed, the realistic limit might extend to our nearest stellar neighbors, journeys of years to decades from the traveler's own perspective, though representing potentially much longer spans of time back on Earth. And with the most extreme, almost speculative technology imaginable, a sustained relativistic rocket capable of near-light speeds maintained for years, the theoretical limit. In terms of distance reachable within a single human lifetime of subjective experience, could extend to thousands or even tens of thousands of light years, a meaningful portion of our own galaxy, though at the cost of returning, if returning is even still meaningful, to an Earth transformed beyond recognition by the tens of thousands of years that would have passed in our absence. And beyond all of that, beyond every tier of technology we can currently imagine or even theorize about, lies the absolute final boundary, the cosmic event horizon, somewhere around 16 billion light-years distant, a boundary that no propulsion system, no matter how advanced, no matter how patient, could ever cross. Because the universe itself is expanding too quickly to allow it. It's a strange thing to arrive at an answer that's simultaneously so enormous and so definite. Enormous, because the theoretical reach of a sufficiently advanced human traveler, given relativistic time dilation, could span a meaningful fraction of our entire galaxy within a single lifetime. A thought that should honestly leave you with a little shiver of wonder before you drift off tonight. And definite, because no matter how advanced we become, no matter how many thousands of years of technological progress lie ahead of us, there remains a hard, mathematically certain boundary baked into the structure of space-time itself, beyond which we, or anyone, or anything, can simply never go. There's something quietly beautiful, I think, in that combination. The universe is not infinite in its accessibility to us, and yet the portion of it that remains accessible, even using only the laws of physics as we currently understand them, is so staggeringly vast that no human being could ever hope to explore more than the tiniest fraction of it, even across a lifetime artificially extended by the strange gift of relativistic time dilation. We are, each of us, impossibly small, set against a backdrop that stretches not just farther than we can travel, but farther in significant part than we could ever travel, even in principle, even with limitless time and limitless ambition. And yet here we are anyway, lying quietly in the dark, minds reaching outward across that very same vastness, not with rockets, but with curiosity, with imagination, with the simple, remarkable fact that a species born on one small, warm planet somehow learned enough about the universe to calculate, with real precision, the very edges of where it could and could never go. That, perhaps, is its own kind of answer to tonight's question. We may never personally cross the gulf to Proxima Centauri, let alone the edge of the observable universe. But in asking the question, carefully, honestly, and with real curiosity, we've already travelled somewhere meaningful. We've stretched our understanding outward across distances our bodies will likely never cross, and in doing so, we've made the universe, just a little bit, feel like home. Let's slow down even further now, because we've covered an enormous amount of ground tonight, or perhaps more accurately, an enormous amount of space, and it's worth gathering it all gently together before we let it settle. There's a funny little irony buried in everything we've discussed tonight, one that's worth smiling about quietly in the dark. We've spent the better part of 2 hours discussing how to travel unimaginable distances using rockets, nuclear pulses, antimatter, laser sails, and relativistic time dilation, and yet the single most efficient way for any of us to visit Proxima Centauri, or the center of the galaxy, or the very edge of the observable universe, tonight, right now, costs no fuel whatsoever. It simply requires closing your eyes. The imagination, it turns out, is the only vehicle currently capable of crossing the cosmic event horizon. No propulsion system required, no exotic matter, no centuries of patient engineering, just a willing mind, a quiet room, and the simple, generous willingness of physics to let us calculate, with real precision, distances and journeys that our bodies will, in all likelihood, never personally make. There's something worth appreciating, too, in just how much of tonight's exploration turned out to hinge not on some single dramatic barrier, but on a series of smaller, almost mundane limitations, stacking gently on top of each other, the way small stones build, slowly into an enormous wall. Fuel is heavy, and heavier fuel needs more fuel to move it, which needs more fuel still. Bodies are fragile, evolved for one gravity, one atmosphere, one magnetic field's worth of radiation protection, and they protest, quietly but persistently, when removed from those conditions for too long. Minds need connection and conversation and the comforting presence of other people, and grow strained across years of isolation in ways that no amount of clever engineering can fully solve. And space itself, the very fabric we're trying to cross, is gently, relentlessly stretching, adding distance even as we try to subtract it. None of these limitations are dramatic on their own. None of them are the kind of single towering obstacle you might picture in a film, an asteroid field to dodge, a villain to defeat. They're patient, quiet, persistent limitations, the kind that simply accumulate, the way fatigue accumulates across a long day, until eventually they add up to genuinely enormous barriers. And maybe that's a comforting way to think about limitations in general, not just cosmic ones, but the ordinary, everyday kind we all carry around with us. Big walls are rarely made of one single brick. They're built slowly from many small ones, stacked patiently over time. Which means gently that big walls can sometimes be taken apart the same way they were built, one small brick at a time, with patience rather than one dramatic, all-or-nothing push. We've also tonight brushed up against a particular kind of humility that space tends to offer anyone willing to sit with it for a while. It's easy, in ordinary daily life, to feel like the center of the world, like our concerns, our schedules, our small daily dramas are the most important things happening anywhere. And they are important to us. and that's perfectly fine. But there's something quietly recalibrating about learning that the very edge of where we could ever travel, even with limitless future technology, even with a spacecraft capable of bending time itself in our favor, still falls staggeringly short of the universe's true size. 16 billion light years marks the edge of where we could ever go. The observable universe itself stretches further still, and many cosmologists suspect the universe beyond what we can observe extends much further again, possibly even infinitely, in ways we may never be able to measure or confirm. We are, all of us, living out our entire lives within a space so small relative to the whole that if the observable universe were the size of the Earth, the entire region we could ever hope to physically reach, even with perfect future technology, might be smaller than a single country, a small dot on a globe otherwise covered in oceans and continents we'll never see, let alone visit. And yet here's the gentle, warm thought to carry with you as your eyes grow heavier. That small dot, that single tiny country on the otherwise unreachable globe of the universe, happens to contain everything that has ever truly mattered to any of us. Every person you love, every sunset you've ever watched, every quiet, ordinary evening like this one, lying comfortably in the dark, letting your mind wander gently outward toward the stars before drifting off to sleep. The universe may be unimaginably larger than anything we could ever reach, but the small portion we do have access to, the only portion that's ever really been available to any living thing we know of, is extraordinary enough to fill 1,000 lifetimes with wonder, and we've barely begun to explore even that. Consider for a moment gently how strange and wonderful it is that a species of curious primates, evolved originally to track fruit trees and avoid predators on the plains of one small continent, on one small planet, eventually grew curious enough and clever enough to calculate the exact distance at which the universe itself becomes permanently unreachable. We didn't need to travel there to know it exists. We simply needed to look up, ask careful questions, and listen patiently to what the universe was willing to tell us. Through light, through gravity, through the small, careful instruments we built to listen with. That's a remarkable inheritance to carry, isn't it? Long after tonight ends, long after you've drifted off to sleep, that knowledge will still be true, quietly waiting, the way all good knowledge waits, patient and unchanged, for the next time your mind wants to wander back out toward it. So as we begin to close tonight's journey, let's bring it gently back down to earth, in every sense of that phrase. We started at the moon, 3 days away, already visited by human feet. We moved through Mars, 6 to 9 months away, well within our grasp in the coming decades. We pushed outward past Jupiter, Saturn, Uranus, and Neptune, watching the timescale stretch from years into decades. We crossed the quiet, icy expanse of the Kuiper Belt and the distant, barely understood Oort Cloud, watching decades stretch into tens of thousands of years. We stepped finally into interstellar space, toward Proxima Centauri, watching our most optimistic theoretical propulsion systems shrink that 100,000-year journey down towards something resembling a human lifetime, with the strange, beautiful help of relativistic time dilation. And we pushed further still toward the absolute, mathematically certain edge of where anything could ever travel, the cosmic event horizon, some 16 billion light-years distant, A boundary not of insufficient technology, but of the universe's own fundamental structure. That's the real answer to tonight's question. Not a single number, but a layered, generous, honest one. Humans could, with current technology, comfortably reach Mars, and with patient effort, the outer planets. With advanced but plausible future technology, we could reach our nearest stars within a working lifetime. With extreme, currently theoretical technology, harnessing the strange gift of relativistic time dilation, a single human lifetime, as experienced by the traveler, could theoretically stretch across a meaningful portion of our galaxy. And beyond all of that, beyond every tier of technology we can presently imagine, lies a final, absolute boundary written into the expansion of space itself, that nothing, not light, not matter, not human ambition, could ever cross. It's a big answer for a big question. And it's exactly the kind of answer that deserves to be carried gently into sleep, rather than chased anxiously towards some neat, tidy conclusion. Some questions aren't meant to be solved so much as held, turned over slowly in the mind, the way you might turn a smooth stone over in your palm, simply enjoying its shape, its weight, its quiet, settled presence. So let your mind rest there, gently, on that smooth, settled stone of an answer, for as long as you'd like tonight. If you're still awake even a little, take one more slow breath in and let it out even more slowly than it came in. Feel the weight of your body, heavy and comfortable, exactly where it's resting. There's nothing left to figure out tonight. The numbers are calculated. The distances are measured. The boundaries, both the soft technological ones and the hard cosmic ones, have all been gently laid out, one by one, like stars slowly appearing in a darkening sky. You don't need to remember any of the specific figures we discussed tonight, the 4.24 light-years to Proxima Centauri, the 16 billion light-years to the cosmic event horizon, the strange, generous mathematics of time dilation. Let those details drift gently out of focus now, the way distant stars blur softly when your eyes finally grow too heavy to stay open. What matters isn't the precise number. What matters is the feeling underneath it, a sense of scale, a sense of wonder, and a quiet, settled understanding that the universe is far larger than we could ever personally explore. And yet, somehow, impossibly, still small enough to hold everything that has ever mattered to us. Right here, in this one small, warm corner of it. If tonight's journey helped your mind unwind a little, helped carry you gently away from the noise of the day and out towards something larger, calmer, and more patient than ordinary life usually allows, I'd be quietly grateful if you considered leaving a like on this video or subscribing to the channel whenever it's convenient for you, with absolutely no pressure attached. It simply helps these slow, careful explorations of the cosmos find their way to other people who might need exactly this kind of gentle, unhurried company at the end of a long day. But if you've already drifted off, which is after all the whole quiet purpose of this channel, then sleep well, sleep deeply. And know that somewhere out past Mars, past Jupiter and Saturn, past the cold, distant edge of the Oort Cloud, past even the faint patient light of Proxima Centauri, the universe is still there, unimaginably vast, mostly unreachable, and yet, in its own strange and generous way, gently, quietly yours to wonder about, for as long as you'd like, every single night. Good night. We'll be here again next time, ready to wander a little further outward together.